You are about to step into a mystery where science meets the unknown. Imagine an hourglass suspended in the dark, grains whispering from future to past, as if time had a direction you could feel on your skin. Now imagine a physics lab where lasers cross like threads on a loom, and single particles play by rules that seem to unweave that direction. In one experiment, looking now changes what counts as then. In another, the very order of cause and effect becomes a quantum blend. A before B and B before A at the same time. We're trained to think of time as a river flowing one way, carrying causes downstream into effects. But the quantum world keeps sketching eddies and countercurrents in the margins. And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. Tonight we're asking a question that sounds reckless and perhaps necessary. Can quantum physics break time? Or does it reveal that time was never as rigid as we imagined? Stay with me, because the core mystery is not whether clocks can run backward, but whether the foundations of reality even need a clock to begin with. Our story starts in the early 20th century, when two revolutions met on the same stage. Einstein taught us that time is stitched to space, stretching and slowing with motion and gravity. Meanwhile, quantum mechanics arrived with a wave function that evolves smoothly until a measurement is made, at which point probabilities sharpen into facts. The first hints that time could be stranger than a tick-tock came not from science fiction, but from tabletop puzzles. In delayed choice experiments, suggested by John Wheeler, you can decide after a particle has passed a fork whether to ask it about its path or its wave-like interference. In quantum eraser variations, you can hide or reveal which path information late in the game, changing the patterns that show up when you sort the data, without sending messages to the past or violating causality. These were warnings, not loopholes. The quantum book of events is written in correlations, not in isolated facts. But the warnings landed like rumors that time's order might be negotiable. To understand what break time could even mean, we should open the machine room. The Schrödinger equation, the law that moves a quantum state forward, does not care about direction. It's reversible. In principle, if you could isolate every particle and flip the phases just right, you could run the movie backward and no one would know. But practical quantum systems are never alone. They brush against air, light, and each other. This steady entanglement with the environment produces decoherence, the process by which delicate superpositions turn into robust, classical-looking outcomes. Decoherence doesn't introduce a new law. It explains why the arrows we see, milk mixing into coffee, memories forming in one direction, measuring devices recording definite results, align with rising entropy, the thermodynamic arrow. Time's one-way feel, then, is not so much carved into the equations as it is painted onto the boundary conditions. The universe's early state was improbably smooth, and from that smoothness flows the gradient we call later. If the basic evolution is reversible, what in quantum physics ever challenges time's order? Start with the quantum Zeno effect. If you keep asking a fragile system the same question, are you still here? Often enough, you can freeze its natural change. It's as if time stutters under interrogation. Stop asking, and the system races ahead or even decays faster. The anti-Zeno effect, depending on the details. Then there is indefinite causal order, a phrase that sounds like a paradox and turns out to be a laboratory reality. Using a quantum switch, you can put the order of two operations into a superposition. A then B, and B, then A at once, and show that the outcome cannot be modeled by any fixed sequence. No grandfather paradox lurks here. You can't send a note to your younger self, but you can perform information processing tasks more efficiently than any classically ordered circuit allows. The lesson is sharp. While macroscopic time keeps a cue, quantum operations can sidestep the velvet rope without causing a riot. At another edge are genuine violations of time reversal symmetry. Certain particle processes in the weak nuclear interaction do not look the same when played backward. These are tiny asymmetries, far removed from coffee cups. But they remind us that time reversal invariance is not sacred everywhere. Even so, those effects don't hand us a practical way to reverse aging or unscramble eggs. They tell us that the deep laws have an anisotropy, an arrow, that coexists with quantum reversibility and thermodynamic drift. And then, there are the experiments that tempt headlines. In delayed choice setups, when you choose to erase or reveal which path information after a photon has been detected, the interference patterns you see in the sorted data appear or vanish accordingly. It feels like the future reaches back. But the urge to say retro-causality should be checked. The total unsorted record on the detector is always the same. You haven't altered the past. You've altered which story you can consistently tell about it when you include all the records. Quantum mechanics is ruthless here. It lets you play with correlations that mimic temporal flexibility while guarding causality with steel bars. Still, possibilities proliferate. Some physicists have explored interpretations where the future helps define the present. The two-state vector view treats a quantum system as guided by a state evolving forward from the past and another evolving backward from the future, meeting in the now. The transactional picture imagines waves that go both ways in time, with handshakes sealing actual events. These frameworks rephrase quantum oddities into time-symmetric stories. They don't change predictions, but they change how your mind holds the movie. Pros: a clean symmetry in a sense that measurement is less special. Cons: they invite confusion with literal backward influence and are difficult to distinguish empirically from more mainstream accounts. Other boundary-pushing ideas live where quantum theory meets gravity. In many approaches to quantum gravity, time isn't fundamental. The Wheeler-DeWitt equation, the candidate law for the whole universe, looks timeless, a statement of constraints rather than evolution. How, then, do we get the flow we experience? One answer: time emerges from correlations. In the Page-Wootters mechanism, you split the universe into a clock and the rest. The total state is static, but if you condition on the clock's hand, the rest evolves relative to it. Another answer: the thermal time hypothesis says the arrow arises from the state of the world itself. Given a statistical state, you can define a time flow as the way that state looks most natural. In holographic dualities, where a gravity theory in a volume corresponds to a quantum theory on its boundary, time in the bulk can map to properties like entanglement and complexity on the edge. None of these break time. They replace it with relational structure, and then show how something like time grows back. Some speculations, by contrast, ask bluntly about time travel. General relativity admits solutions with closed time-like curves, loops where a traveler meets their younger self. Quantum mechanics responds with models that try to keep the mathematics consistent. In one version, self-consistent histories conspire so that you can't create paradoxes. In another, interactions with a time loop look like a noisy quantum channel. These models are interesting thought experiments, useful for thinking about what consistency means. But we have no evidence that nature gives us macroscopic loops. And we have plenty of reasons to suspect that quantum gravity will forbid them or quarantine them in regimes we can't access. The universe seems to prefer puzzles without contradictions. Returning to the lab, the quantum world keeps showing us ways to bend our intuitions. Time crystals, phases of matter that break time translation symmetry, sound like perpetually ticking machines. But the versions we've realized are driven systems that settle into rhythms with a period different from the drive, a kind of temporal order emerging in steady oscillations. They don't give you free energy or a clock that runs without a battery. They give you new ways matter can organize in time, like crystals do in space. Weak measurements let you peek at a system without blasting it into a definite state, accumulating gentle information over many trials, and reconstructing aspects of the evolution that would otherwise be hidden. Loschmidt echoes, the attempt to reverse a system's dynamics, show how quickly tiny imperfections make reversibility decay, a practical arrow sprouting from tiny seeds. All of this erases a sharper version of our question. Does quantum physics break time? If by break we mean shatter causality and let messages leak into the past, the answer is no. Experiments designed to tease retrocausal behavior always keep faith with no signaling theorems. You can't send winning lottery numbers to yesterday. If by break we mean reveal that time's order and even its necessity are more context-dependent than classical experience suggests, then the answer looks like yes. Quantum theory allows superpositions of orders, reversible dynamics knitted to irreversible records, and relational notions of time that get their meaning only from subsystems. It invites the idea that time's river is an emergent large-scale current flowing over a quantum landscape, where small streams meander and sometimes loop. That landscape complicates the era we live by: memory. Why do we remember the past and not the future? Physics doesn't forbid a brain that remembers tomorrows, but the statistical mechanics of a low entropy beginning suggests why such beings are vanishingly unlikely. Records form as correlations spread outward, from glass shards to footprints in dust to photons streaming from a burning star. In a world that started orderly, those records pile up in one direction and are eaten by entropy in the other. Quantum mechanics adds a twist. Records are redundant when many fragments of the environment carry the same information about a system, letting multiple observers agree on facts. That redundancy, sometimes called quantum Darwinism, is another way the arrow shows up. Information about certain stable properties proliferates forward. Where, then, is there room for us, decision makers, storytellers, in a cosmos where time is both rigid and loose? Perhaps in the gap between fundamental reversibility and practical irreversibility. The space where choices matter is the space where microscopic alternatives get amplified into macroscopic outcomes. Which path your career took, which friend you called, which invention caught on. All of those are sensitive to noise and initial conditions, but also to intent and coordination. Quantum physics doesn't erase meaning. It deepens it by showing that reality's final facts are co-authored by dynamics and context. Let's gather the major possibilities and their pros and cons. First, the orthodox view. Quantum dynamics are time-symmetric. Measurement plus decoherence and low entropy initial conditions give you the arrow. Causality is safe.
It is conservative and extremely successful. But it leaves some aching questions about why the beginning was so orderly. Second, time-symmetric interpretations. They restore elegance by letting boundary conditions at both ends speak, reducing measurement's mystery. They offend no data, but can be misunderstood as endorsing literal backward causation. Third, indefinite causal order. Not a worldview, but a resource. It shows that before and after can be operationally fuzzy, improving computation and communication tasks in principle. It does not break causality, but it breaks the classical assumption that all processes can be embedded in a single global order. Fourth, emergent time. In quantum gravity, time may be a derived quantity. This is a fertile, unfinished garden, rich in ideas, low on decisive experiments. Fifth, time travel and closed time-like curves. Mathematically intriguing, physically doubtful, ethically terrifying if real. So far, they're mirrors that reflect consistency requirements back at us.
Why does any of this matter for more than curiosity? Because time is the stage for meaning. Our laws tell us how worlds could be. Our arrows tell us how worlds unfold. If time's flow is emergent, then so is the arena where responsibility and hope live. If quantum processes can loosen the order of operations, maybe there are future technologies, sensors, networks, computers that work with time as a resource rather than a constraint. If the arrow depends on initial conditions and record-making, then stewardship of memory, archives, education, culture aligns with physics. The ways we build redundancy into our collective knowledge are the ways we push against forgetting. Step back to the hourglass. It hasn't shattered. It has become a kaleidoscope. Tilt it and new patterns emerge. Rotate it and you see repetitions you missed. Peer too closely and the grains blur into a haze where before and after lose footing. Quantum physics didn't break time. It broke our certainties about what time must be and offered a subtler picture. A reversible micro-law entangled with irreversible histories. A strict prohibition on paradox wrapped around a playful looseness and order. A timeless foundation that gives rise to clocks whenever correlations can play the role of hands. That is a deeper, not a shallower mystery. So I'll end with a question for you to carry into the comments. If time is partly a story reality tells about itself, rigid enough to keep paradox at bay, flexible enough to let order blur, how would it change the way you live to think of your choices not as tiny boats tossed on a river, but as small acts of navigation on a sea where currents are real, eddies exist, and maps are made as we go?